All right, so let's start. Hello, everyone. So today is the lecture number 5. And we will continue to discuss linear regression, okay, because as I said, even if it's probably the simplest machine learning technique you can think of, it's also one of the most used and powerful in many cases. Okay, so let me just recall a bit what we said yesterday, and then I will move on to new things. Especially, I will discuss the probabilistic interpretation of the least square estimator and the ridge estimator and the lasso estimator that we discussed. We'll see how we can understand these approaches from a probabilistic point of view using Bayesian Inference. And then I will solve some exercise that I asked you to look at, which are in the notebooks. And then we will do some numerical experiments, and that will be all for today. Okay, so let me recall what we said. We studied 3 types of linear regressions. Okay, so there is the most basic one is ordinarily square. Okay, where your estimator, your learned parameters, are solving the following optimization problem. This is your training data, W minus the labels in the training data, and this is the norm2 squared. Okay. What we said is that the advantage of this estimator, one big advantage is that you don't really need a numerical solver to solve this optimization problem, because you can get the solution by hand, and you just need to take the gradient of this convex function and equate it to 0. This will give you the solution, and the solution is given by x transpose x minus 1 x transpose y. Okay, and again, I'm not writing everywhere train. I mean, x and y here should be understood as the inputs and outputs in the training data. Okay, I also mentioned something important, is that even if this method is linear, it is linear in W, okay, in the sense that the model that you assume is a linear function of W. The model you assume are linear combinations of the features, okay, and you're trying to learn the vector of coefficients. But this does not mean that the method is restricted to learn linear relationships between inputs and outputs, because again, you can redefine a new data set, okay, where some columns, let me denote a column like this. The column J could be whatever function you want of some other column of features of the original data. Okay. Let me call it, let's say, column J as well. So you can expand your data set by taking features that you already have access to, okay, and then create new features by applying whatever function you want, where phi here applies pointwise. Okay, it's a function that applies pointwise. It can be a polynomial, it can be a sine, it can be much more complicated functions. But so you can expand your data set, okay, in the way you want. And because this phi, this function here, is not necessarily linear, then you can include, if you want, non-linear features in your model. The model at the end will be linear combinations of these new features, but still you have this degree of freedom that can be exploited. Okay, so it's at the end extremely generic. This method is very powerful. Okay, one problem with this technique here that we see directly is that this estimator is only well defined when the rank of the matrix X transpose X is P. Okay, recall that the matrix X is of size the number of samples in the training data times the number of features. Okay, so this matrix is of size P times P, and to be able to invert it, you need that it is non-singular, which means that all the eigenvalues of this symmetric matrix are non-zero, which again means the same as the rank being equal to the dimension of the matrix. Okay. So this is generally the case because usually you have more data than features. Okay, but and these features are generically, let's say, independent enough of each other, so they are linearly independent, which implies that you would get that this condition is verified, but this is not always the case. And one way to solve this issue is to introduce ridge regression. Okay. And not only it solves this issue, which occurs when this matrix is ill-defined, okay, when you cannot invert this matrix, but also it's a way to reduce the complexity of your model and therefore to reduce overfitting. Okay, so the ridge solution, okay, recall, it's the same cost, except that we add a penalty, which comes in the form of the L2 norm of the estimator. Okay. And we said, so this is the unconstrained formulation, and this is equivalent to finding the argmin with respect to some W in RP, such that W has the norm 2, which is less than some constant that depends on lambda. Okay. Of just the usual least square cost. Okay, the square cost. Okay, these two formulations are the same. And we understood that this ridge, the solution of this optimization problem is similar to the least square solution, except that the coefficients are scaled down, okay, by a factor that depends on lambda, the penalization strength here. Therefore, you are constraining the modulus of your coefficients, and effectively you are reducing your hypothesis class, which may lead to a decrease in overfitting, and we observed that numerically. Okay. And then we discussed another type of regularization, which is called lasso or L1 penalty. Okay, and the advantage of this one, we said, is in terms of interpretability, because the solution of the following optimization problem, the penalized optimization problem, where now we have a L1 penalty on the norm, which is again the sum of the absolute values of each component, tends to, so the solution of this optimization problems tends to have many components equal to 0. Okay. Did I discuss the graphical representation, the graphical interpretation of that? I'm not sure now.
Yes, yes.
I discussed it with a. Okay,
in lasso.
Okay, so this is equivalent. to the same formulation. Okay, again, where now the norm is less than certain t that depends on lambda. So did I discuss this? This picture here? No, huh? I don't think I discussed that picture. So let me discuss.
I remember the one above.
Above, we discussed that. Yeah, okay.
Yeah.
Yeah, so let's, okay, here was a graphical representation of the operation that the lasso is doing on the least square estimator. Essentially, it threshold the coefficients that have an amplitude less than lambda to 0, and the ones that have an amplitude greater than lambda, it scales, it shifts them by a factor lambda, okay, down or up, depending if it's a negative or positive coefficient. But what is important is that all these coefficients in the least square solution that were less than, that have an amplitude less than lambda, are set to 0. Well, for the ridge, it was really a global factor 1 plus lambda that reduced the magnitude of the components, but none of them is really set to 0. Let's see another graphical interpretation of what is going on that I like very much. This is the one I understand the best. So, okay. So let's write down here the lasso once, okay. And I will write the constraint optimization version, okay? So it's over any W such, well, sometimes there are bugs like this. Any W such that the norm 1 of W is less than some constant t, okay? Of the square cost plus nothing, because this is the constraint optimization version, okay? So let's try to understand that there is a competition between two things here. There is a competition in the fact that we want to reduce this quadratic cost, which is here, okay? But at the same time, we require that the solution belongs to a certain subset of all RP, all the reals, the p-dimensional space, okay? And this subspace is defined by the L1 norm being less than a constant. And actually, if you draw, for example, in 2 dimension, so this is R2. If you draw all the vectors, okay, you draw the region in which vectors do have a norm less than t, a L1 norm less than t, it defines this sharp region, okay? All the vectors that are inside here verify this constraint, okay? All right, so the solution has to belong to this region, but at the same time, we want this cost to be minimized. We know that if we forget this constraint here, this L1 constraint, the solution is the least square solution. So let's say that the least square solution is here. Okay, this is this W hat. It is a W hat least square. Okay. So now what happens is that this optimization problem is forcing you to go away, to move away from the least square solution, because you have to belong to this region here. But at the same time, you want this cost to be, this quadratic cost to be as small as possible. In a sense, you don't want to be too far from the least square solution. Okay. So what happens is that you cross, the solution will be here, and will be the first intersection point between what's the name of this? You draw the contour lines. So a line like this around the least square solution means a set of points where this cost here is constant. Okay, so as you move away from the least square solution, this cost, this quadratic cost, is increasing. Okay, so you increase this cost until you reach a point which is an agreement with this constraint. So you are in this region, and because the L1 constraint set defines a region with corners. This is really coming from the fact that you are taking a L1 norm. You are considering absolute values, sum of absolute values of the components. It's like a diamond. You have to imagine that in much higher dimension. It's like a diamond, this region with many corners all around. Okay. And while these contour lines, instead, around the least square solution, they are like ovoids, they are like ellipsoids. Why are they like ellipsoid and therefore smooth? Because this is a quadratic loss. It's a quadratic function. Okay, so it does not have corner. It's something which is smooth. It's like a ball, an ellipsoid. So when you cross an ellipsoid with a diamond, with high probability, it will touch at a point which are corners of the diamond. And what does it mean to be at a corner here? It means that some components are zero. In this case, the component 1, W1, would be 0. Okay? So this is why the lasso penalty, the L1 penalty in the lasso estimator is enforcing many components to have value equals 0. Okay? Now, if you do the same reasoning, but for ridge regression, the picture is different. We have again the contour line around the least square solution. Okay, and now the region in the ridge regression, instead the optimization problem that we are solving, the constraint optimization problem, is an argmin with respect to all w's such that their norm 2 is less than some t. Okay, of the same thing. And the norm 2 again defines. What does it define this? It defines a ball. Okay, this is the definition of a ball. The norm 2 being less than something. And here is our ball in 2 dimensions. It's a disk. And if you approach an ellipsoid, which are the contour lines around the least square solution from a disk or from a ball in higher dimension, because you are touching 2 smooth functions with high probability, they will touch at a point which is like an arbitrary point on the surface of this ball. Okay, so there is no reason that you will cross exactly at a point where some components are 0, in contrast with the lasso, which is here. Okay, so that's why some components like this, the W1 here, will be set to small values. Okay, but not 0. Okay, so you are constraining the entries of your vector to have a small amplitude, but not necessarily 0. That's really the geometric interpretation. Okay, which I think is very nice. Okay, so this is what we discussed. Now, what I would like to do is to understand these three approaches, these 3 linear regression approaches in terms of probability. Okay, to give a probabilistic interpretation to these things. So let's try to do that. So let me first do a very short, like a one page introduction to Bayesian inference. Okay, for those who are not familiar with Bayesian inference, I strongly advise you to have a look just spend a bit of time understanding that this is extremely important as a scientist to know in any science. Okay, so let's say you have, so right now we do a parenthesis. And I'm not directly considering this linear regression estimators. Okay, I'm just talking generically about Bayesian inference, and then I will specialize. Okay, but let's say generically that you have some parameters. Okay, so okay, maybe let's use the notations. Let's match a bit the notations. Say you have some parameters theta, which are unknowns. Okay, and there is some process that generates data according to some random process that maybe you know precisely, maybe you don't know precisely, but there is a link between this, which is the data, and this, which are unknown parameters. Okay, this can be vectors, a scalar. Okay, it doesn't really matter, and this is a process, usually a random process. Okay, this arrow represents some random process. Okay, so when you do probability, and generically you can always model a process like this using a probability distribution. Okay, and the probability distribution you need is so-called conditional probability distribution. It's the probability that you observe, that you obtain some y, given that the unknown parameters take a value of theta. Okay, so maybe this probability distribution here is really fully capturing this random process. Okay, maybe the y's were truly generated according to this probability distribution, which is conditional on these unknown parameters that we're trying to infer. But maybe not. Maybe this probability distribution that you will use to perform inference can be a model of the true random process. And this is usually the case in science. Okay, we use models, but maybe this model is let's say, is well capturing this random process, or maybe it's a coarse, quite rough model, but this is what you will use. Okay, this describes the link between data and unknown parameter. And this probability distribution, this conditional probability distribution, is what we call the likelihood. Okay, and likelihood in the sense that this is the likelihood of observing the data y that you obtained, given that the unknown parameters were some value theta. Okay, so if this likelihood is high, then maybe the unknown parameters, given that you observe this realization of the data, maybe these parameters actually take the value that lead to a high likelihood. The likelihood is very low. Maybe this should not be the good parameters. Okay. All right. But maybe you also know something about these unknown parameters. You don't know their precise values, but you know some specific things about it. I don't know, some characteristic. For example, you know that these parameters are, let's say, bounded between -1 and 1, or that they follow a Gaussian distribution, or I don't know, that they are necessarily positive numbers, or whatever, or they have many components. If it's a vector that is 0, okay, you can assume many different things, and you can also represent that in terms of a probability distribution. And this probability distribution is called the prior. Okay, in the sense that this represents your a priori information about these unknown parameters, a priori in the sense before you observed any data. Okay, this distribution does not depend in any way on the data. Okay, And again, this distribution can be really the probability distribution from which were generated these unknown parameters, or maybe it's simply a model. And again, most of the time we are in the second situation where this is a model that we use. Okay, the real world is extremely complex, and it's hard to really represent using simple tractable probability distributions, things that happen in nature and in the real world. Okay, so often you use models. Okay. Okay, so this is your a priori distribution. Now, one important thing to keep in mind is that once you measure the data, okay, this data that depends on the unknown parameters, okay, implicitly through this random process, you should never change the prior, in the sense that if you have some a priori distribution, you suppose things about the unknown parameters, and let's say you obtain data, and this data does not really fit what you expected, in the sense that it seems to contradict in some way the prior assumptions that you were doing. Okay, still you should never change the prior a posteriori. Okay, otherwise what you would do is actually this prior distribution would become a function of the data itself. And this you should never do. Otherwise, it's not a prior anymore. You are introducing bias, in the sense that you are refining your a priori assumptions given the data, while this is not what you should do. What you should do to combine your prior assumptions and the likelihood, which captures the information, the additional information you got from the data, is using Bayes formula. Okay. So the Bayes formula tells you that the probability distribution of the unknown parameters given the data, okay, is given by the product of the likelihood, so the probability of the data given the unknown parameters, times the prior distribution, divided by a normalization. Okay, so normalization is the integral with respect, so this is a probability distribution over theta, so you need to integrate over theta. Okay, I put a prime just to emphasize that this is a dummy index. Okay. And this normalization here is nothing else than just the probability of the data itself independently of the unknown parameters. And this is called the evidence. Okay. All right, so why is this probability distribution so important? So this is the a posteriori distribution, or just posterior distribution. Because this posterior distribution combines in a single compact probability distribution that can be arbitrarily complex, but still you have defined a probability distribution that completely encompasses all the knowledge that you have about the unknown parameters. Okay, it combines in the proper way your a priori assumptions, okay, that come in the form of the prior, with the information that you gained from the data, which is coming in the form of the likelihood. Okay, and this likelihood again is modeling, is your model of how the unknown parameters are connected to the data, or vice versa, actually. Okay, how the data is related to the unknown parameters. Okay, and so this probability distribution will allow us now to select some values for the unknown parameters. We will see how. This is called Bayesian decision. It's called making a decision, how to select an actual value for the parameters using the posterior distribution. But it's not only a way to select actual parameters, it also contains information about your uncertainty about the unknown parameters. You see that if this, let's say that, let's say for a moment that this unknown parameters that we are trying to infer is a scalar, okay? It's just a real number, okay? So I can plot like this. And now I'm plotting the posterior distribution. And let's say, so this, let's say I can completely compute this probability distribution. And let's say it looks like this. Okay, over a very wide range of value, let's say minus 1,000 here, and we have 1,000 here. This is not very informative, okay? In the sense that, okay, you look at this probability distribution, it's hard to say which value for the unknown parameters you should actually select, right? Because the distribution is rather flat, okay? But still, it is important to see that, because then it tells you that, yes, the posterior distribution is not so informative, but this means that given the data that you have access to, and given your a priori assumptions, there is simply not enough information contained in this data and in these assumptions to make proper inference about the unknown parameters, okay? So it gives you a quantification of uncertainty, okay? So one way, for example, to capture this uncertainty into a single number could be to compute the expectation with respect to the posterior distribution of theta squared minus the expectation of theta squared, which means the variance of theta with respect to the posterior distribution. Okay, if this variance is large, so then the fluctuations of your posterior are large, so it's hard to draw conclusions. Now, instead, let's say you are in a second situation. So here the variance would be typically large. Now let's say that instead the probability, your posterior distribution looks like this. Okay, or even more extreme. Okay, it becomes much more natural to pick a value which will be closely close to the mean here, for example. Okay, now you plot the posterior and you know that given the data you have and your assumptions, your uncertainty about what should be the parameters is low, and so you can make decisions. You can pick a value for the theta with confidence. Okay.
Sorry, I have a question.
Yes.
Here you are changing the likelihood or the prior distribution to find the best solution.
No, the prior distribution and the likelihood are fixed. Okay, once you measure the data and you chose a model for how the parameters and the data are linked, you define the likelihood once for all. Once you made your assumptions about what the parameters should be independently of the data, you fixed your prior, and using Bayes formula, you obtained your posterior distribution. Okay.
Yes, so you have now a posterior distribution and you want to make it more condensed about...
No, you cannot make it more condensed. The posterior distribution is what it is, okay? What I was drawing here are three cases, are three different posterior distributions. Let's say this one, the black one, is a posterior that you could have obtained if you had a very small amount of data or very noisy data, okay? Almost no data of bad quality, so the posterior is not picked at all, okay? It does not contain enough information. This would be a posterior that you could get if you had access to much more data and of much better quality, or if your prior was much more, much better capturing the actual distributions of the theta. Okay, so I'm just plotting three different instances of posteriors. Okay, I'm not changing anything to make the posterior better. Given the data and the prior, the posterior is fixed. Okay, you cannot change.
Right. Thank you.
Okay, these were 3 different posteriors in 3 different settings, and this third setting here looks like a posterior which is much more peaked, and therefore we are much more confident in the decision we will make. And the decision means picking an actual value for the theta. Okay, so how do we make decisions? There are many ways. Okay, once you have your posterior, you can select you can pick a value for the unknown parameters in many different ways, but there are 2 main ways. Okay, the first one is to select. Okay, put a hat to mean the one you select, the one you pick from the posterior, is theta hat to be the mean of the posterior. Okay, that I denote simply like this. Okay, all right, this estimator is a good estimator. It's actually called a Bayes estimator, and it's also called the minimum mean square estimator, and it minimizes the expected deviation, okay, between the true parameters, the unknowns, and your estimator. Okay, but let's forget that. This is the Bayes estimator. This is the mean. Okay, it's very natural to take the mean of the distribution. Okay, but the problem with this decision is what? The problem is that you need to compute the posterior, and this can be extremely problematic. Why? Because we look at the formula here. Okay, our Bayes formula. You see that one difficulty is what can be the difficulty, actually the unique possible difficulty in computing this probability distribution. Okay, so no clue.
Just the prior.
So can you be more precise?
You have to have a good choice for the prior.
Yeah, but let's say you made a choice for the prior. Well, like computationally speaking, if you try to compute this posterior distribution, what can be the issue? Say you have a sorry?
The evidence?
Yeah, exactly. It's to compute the normalization. It's to compute the evidence. You see that you have an integral at the denominator. So for those who are physicists here, this is very similar to computing a partition function. You have to imagine that here I plotted things for a scalar theta, okay? But you have to imagine that when we do Bayesian inference in modern applications, the type of the parameters that we want to learn, okay, the theta, are extremely high dimensions, dimensional objects, okay? So this integral here typically is an integral over Rm, okay, where m is the dimension of your parameters, and m is very large. So you have a very high dimensional integral to compute, exactly like you want to compute a partition function in statistical mechanics, okay? And this is hard, we know it. So you can use Monte Carlo, you can use different techniques, but usually it's extremely costly from a computational point of view, okay? So the problem is to compute the evidence, okay? What is the second type of decision you can make that avoids this problem? And that is also quite natural if you look at this drawing here. what is a natural choice if it's not the mean? Okay. What would you think of? And that avoids this problem of computing the evidence, where you see the evidence is just a function of the data, nothing else. What could you do?
Maximize the likelihood.
So you could maximize the likelihood. This is one way, but let's say you want really to exploit the posterior distribution. What you do is to maximize the posterior, not just the likelihood. Okay? So instead of taking the mean, you take what we call the mode. Okay? The mode means taking the value where the maximum of the distribution is. So for example, okay, so it's the argmax with respect to theta in Rm. Okay, this is an integral over Rm of the posterior distribution. So let me write down the posterior again. Py given theta, p theta over py. But you see that this p of y does not depend on theta, so we can just forget it when we take the argmax. This is just a constant, it does not change the position of the maximum. Okay, so we can just take the argmax of the likelihood times the prior, and because the likelihood and the prior we can compute them, these are our choices. We don't have to compute complicated integrals or anything to get them. So this decision is simple, okay? And actually what people do is not to take the max, the mode, this is called the mode of the posterior, sorry. I have a bug with my pen. Okay, what people do, which is the same, is to take the mode or the max of the log likelihood. Sorry, of the log posterior. Why is that the same? Because the log is an increasing function, okay? So if you apply an increasing monotone function to a function, it does not change the position of the max. Okay. And this estimator is called the MAP, MAP, estimator for maximum a posteriori estimator. Okay, and this is what actually people do. Okay. All right. What I want to say now. Okay. If, let's say, you don't want to make prior assumptions, or maybe the prior is too complicated for some reason or whatever, you can do something even simpler, is just to take the max of the likelihood. Okay, so final decision, which is not a Bayesian decision, because if you don't include the prior, this is not called a Bayesian decision. This is another type of decision. Is the so-called maximum maximum likelihood estimator. Okay. Again, we take a log of p of y theta. Okay. And this log, we like this log likelihood. Actually, we like to give it another name. Just we invert the role of theta and y. And what is the reason behind that? Because you should really think of this log likelihood here, not as a function of y given the parameters, but really as a function of the parameters for fixed realization of your data. Okay, the data is fixed, you cannot change it. You get it once for all, and so the data play the role of parameters. Instead, the dependency that is important here is in theta, okay? So people just interpret the rule to emphasize this fact that we see the log likelihood not as a probability distribution, the log of a quantity distribution of y given theta, but really as a function of theta that will be maximized in order to get the MLE estimator, which means maximum likelihood. Estimator. Okay. Why do we take logs if it doesn't change anything a priori? What's the reason behind that? Why may it be useful?
It's useful for Gaussian posteriors.
So if you have a Gaussian likelihood or posterior, indeed, you have an exponential form and you take a log and it's easier to manipulate. But you can extend this reasoning. The point is that usually this type of posterior or likelihood distributions that depend on high dimensional parameters, because you have to think of doing all that in high dimensions, not just for scalars. This probability distribution usually depends on their parameters in an exponential way, okay? So you can, these type of distributions are usually very peaked, okay? And may depend on, so for example, if you have binary variables, let's say, okay, the theta belong to -1, 1 to the power n, okay? You have exponentially many configurations, possible configurations for your parameters, okay? And so this type of probability distribution can be extremely sensitive to a change of configuration, and you can have an exponential change in the value of the posterior or the likelihood for two different configurations. And in a computer, you don't want to manipulate objects that diverge exponentially with the parameters like this. So you want to reduce the amplitude of the numbers that you are manipulating on your computer. So you take a log, okay? And what you have in mind is that things depend exponentially in the parameter values, okay? All right, so let's use our understanding to understand now, to interpret, let's say, ordinary least square regression, okay? Ordinary least square. So in ordinary least square, to derive the ordinary least square estimator from the Bayesian perspective, the assumption that is made is the following. What is assumed, okay, so this is our model. This does not mean that the data has truly been generated in this way. This is our choice. This is our assumption. Our model of the process that links the responses, the labels to the inputs is a linear model with additive Gaussian noise. Okay, so the assumption that is made is that the yi's, the labels, are related to the inputs according to a linear relationship, transpose xi, plus Gaussian noise, where the epsilon i's are drawn independently and identically according to a Gaussian distribution with variance sigma squared, for example. Okay, so this is our assumption. This is the model assumed in this Bayesian framework. Okay, and we don't assume anything about the x's, about the unknowns now are these parameters w. Okay, the x's are given to you. This is coming from the data. Okay, so we want to infer according, given that our model of the world is this one, we want to infer the best values for the unknown parameters, the w, that we assume have generated the labels given the inputs x's. Okay, so we do Bayesian inference. Okay, so we want to write down a probability distribution for the unknowns w, given our data. Okay, y, it's the vector of all labels, and the matrix of inputs x's. Okay. Okay, so I use base formula. It is given by, so the x's are always fixed. Okay, these are the inputs. This model here really connects the outputs to the inputs. Okay, so we always fix the x's. So we use base formula. This is the probability of the y given the w and the x's. Okay, times the prior distribution of the w. Okay, divided by the normalization, which is in this case simply the probability of the y given the x's. Okay. So you see the difference with respect to what I did before is just that now there are these x's that are fixed everywhere. Okay. Everything is conditioned on these x's. Of course, here our prior does not depend on the x's. Okay. The a priori, the characteristics of this vector that we're trying to infer should be independent of these x's. Okay. All right. So this is base formula. And now we can write down, explicitly our likelihood, given that the model is what I wrote above. So what is the likelihood in this case? Can someone tell me? So let's say, because we assume that all the noise entries here are independent, okay, then the probability of the y given the w and the x is just a product from I equal 1 to n of the probabilities of each of the yi's, okay, given the w, and each yi depends on a single xi, okay? So this product is coming from this assumption here, that the Gaussian noise is independent for each new point here for each label, okay? It implies this product structure. And what is this likelihood of a single response here, given an input and the parameters? Does someone know? What can I write explicitly here? What I can write explicitly is the probability distribution, the probability density function of a Gaussian, okay? Why is that so? Let me write it explicitly and explain. Okay. Why can I write that? Because the model here, the reason is that writing this where epsilon i's are independent centered Gaussian random variables is equivalent to write that yi is drawn from a Gaussian distribution where the mean is this, okay? And the variance, okay, the unique source of variance here is this one. The variance is unchanged, is sigma squared. Okay, is that clear? Which is what I wrote here. The probability density function here is this. Okay. Okay. Now, let's write different decisions that we can make, starting with the simplest one, which is the maximum likelihood estimator. Okay, so it's the argmax of my likelihood function, okay, given my data. And the likelihood in this case is the log of this product. So this is just the argmax with respect to the W. The log of a product is the sum of the logs. Okay, take the log of an exponential. Okay, so directly you obtain. Okay. This thing, sorry, I took the log, so I have the sum here minus 1/2 log of 2 pi squared. Okay, so I just wrote the log of all this product here. This thing does not depend on W, so I can just forget it. When I take the max, it's just a constant shift. And this does not depend on the W, and it's a global multiplicative factor of this whole sum, which is what depends on W. So I can also set it to 1 without loss of generality. It does not change the position of the max. And so what we obtain is the argmax W of sum over I of minus yi minus W transpose xi squared. And the max of this function where there is a minus is the same as the argmin of the same function without the minus. Okay, I'm just doing a flip of the function, so the max becomes the mean. Okay, if you have a function, you take the mean, you take minus this function. Okay, this is the function, this is minus the function. The position of the max for the function is the same as the position of the mean or minus the function. Okay. And this is exactly the least square estimate. Okay. So the maximum likelihood estimator under a Gaussian model like this, okay, if you assume that the true labels were generated according to a linear relationship like this with additive Gaussian noise, which are independent for each labels, then it's equivalent to assume this likelihood. This is your model for your problem, okay? And then you do the maximum likelihood estimate of that, which is giving you, after simple manipulations, the least square estimate, okay? So this is the probabilistic interpretation of the least square. Is it clear? Yeah, okay. So if it's not, you should tell me. Now, let's understand how to get the ridge, how to get ridge regression, the ridge estimator. You see that the decision we took here was the maximum likelihood estimate. Okay, so I did not take into account any prior I could have. Okay, so now let's introduce a prior in our Bayesian formulation. And let's say that the prior, what prior do you think will lead to ridge regression? Does someone have a clue? No. I recall that in ridge regression, the penalty is an L2 penalty. I mean, it should ring a bell, the fact that here the likelihood was Gaussian and that it led to a quadratic cost, right? So now we want to add a quadratic penalty. So what should be the prior? No clue? Okay. Gaussian, okay. So now I assume that the probability distribution of my parameters, my a priori assumption, is that these parameters were drawn from a Gaussian distribution with identity covariance, which means concretely what is that my prior distribution is a product over the components, which is p-dimensional vector of distributions like this. So I assume that my a priori assumption is that these parameters are independent, which is what I wrote. This is independent. And then I assume that each of them is Gaussian distributed. With zero mean and variance. Let me call it gamma, okay, squared, W squared. And there is a minus. Okay, this is my a priori distribution. It's a Gaussian, a standard Gaussian, centered Gaussian with variance sigma squared. Okay, this is the same as writing that each W is assumed, okay, a priori assumption. To be drawn from a centered Gaussian with variance gamma squared. Okay, and I plug that in. And now what I will do is not anymore a maximum likelihood estimate, but I will do a maximum a posteriori estimate, maximum a posteriori decision. Okay, so I'm maximizing the posterior distribution. Okay. X and Y. Okay. And what is, and again, what I will maximize, not just the posterior, but it's the log, which does not change anything, which means the log of what? Of my likelihood, which is as before on this form. That I can, you know, I can now I did the computation once, I can just write it directly. I write my Gaussian directly in matrix form. Okay, this is my likelihood. times my prior, which reads how? Which reads in matrix form again. It's just the same thing as here. -1/2 gamma squared norm 2 of W. Okay. And of course, there are normalizations. Here, a priori, you should put the normalizations. But again, these are constants. Okay, they do not depend on W, so they will just disappear because we take the argmax. So this normalization does not influence in any way this operations taking the argmax. So I will not write the normalization because it does not change anything. Like here, you remember this normalization did not matter. The normalization of the likelihood. That's the same for the prior. And this is what? This is the argmax respect to W of, okay, -1/2 sigma squared y minus x W squared minus 1/2 gamma squared norm 2 of W. Okay, which is the argmin of the same thing without a minus. And the 1/2 is a common factor, so I can just simplify it. It does not change the position of the max. Okay. And now I can multiply both terms. Okay, I can put a sigma square here in front. Again, this is a global multiplicative factor, so it does not change the position of the max. And therefore, I obtain argmin, sorry, of the minimizer. And here we are. Okay, now I just I call this number, this arbitrary number lambda, and I obtained the solution of ridge regression. Okay, so you see this lambda, this penalization here, controls the ratio between the a priori variance and the variance in the likelihood. Okay. So you see that when you increase lambda, it's the same as saying that gamma is much bigger than sigma. It means that the variance of your prior when you increase lambda, it means that gamma is small with respect to sigma. And gamma being small means that the variance of the prior is small. Okay, the variance of the prior is small, which means that your prior, you have confidence in your prior. Okay, you want to give weight to the prior. Okay, you trust more your prior than the likelihood, if you want. Okay, and this translates into having a lambda bigger, and indeed this is a stronger penalization. Okay. As an exercise, I ask you to think about how to obtain the lasso from a maximum a posteriori decision. So which posterior is it? Okay. which posterior should you define such that the maximum a posteriori decision for that posterior gives you the lasso solution. Okay, so here you have to essentially find which prior you should use. Okay, because this part does not change in the lasso. It means that the likelihood is the same form as before. But here, okay, instead of a L2 penalty, you have a L1. So what is the associated prior that will give you a L1 penalty? And you can rederive all that to make sure you understand, but here the keyword you should look for Laplace prior. Okay. But again, using this Laplace prior, you do a maximum a posteriori decision, and you will see that you get the lasso estimator. Okay. Is there a question? Okay. I have absolutely no idea if I'm just too slow and too clear or if it's pure noise. Anyway, so now I will I want to solve some exercise that are found in the notebook. How to do? Okay, so if you open the notebook free, you don't have to. I will rewrite the questions. I want to solve one question with you, and then to leave the other ones for you. But let's say it's the more technical one, and I would like you to understand how it works so that you can solve the next questions, which are basically done in exactly the same way. So I want to discuss the exercise 1 of notebook 3. So I asked you to have a look, so I hope you did. Okay. So essentially notebook 3 is about, it's the notebook on diabetes. So we already had a long discussion of interpreting the different numerical experiments. I will not come back to that. I did that yesterday. I want to focus on the exercise. So essentially the beginning of the notebook is about recalling you everything I just said today. Okay, so the first question of the exercise 1 is goes as follows. The least square solutions corresponds to the maximum likelihood estimate of which likelihood function? We spent this whole course about solving this question. So the least square solution is the maximum likelihood estimator for the Gaussian likelihood. Okay. Derive the least square solution explicitly from its definition. So essentially the question is how to obtain this thing, and I already did it. Okay, you take the gradient of the quadratic cost that defines the least square problem. You take the gradient equal to 0, and you obtain you directly obtain that. Okay, so this should be clear already. What is a bit more tricky is the next question. So I will consider a realizable setting. Okay, so remember what it means. It means that the model that we assume for doing for our hypothesis class contains the actual model that generated the data, the true hidden model that we don't know. Okay, so what does it mean in the case of linear regression? It means that the true model is also a linear model, okay? And when we do least square, we understood now that the true model that is assumed is actually a linear model with Gaussian noise, okay? And the least square solution is the maximum likelihood estimate for that model. So the true model really that is assumed is this. But here in the realizable setting, it's not only that we assume this form. So, okay, in the notebook, it's the Gaussian noise is called eta. Before I was calling epsilon, but that's the same. It's not only that we assume this linear model, but it's in the realizable setting, the true model is like this. Okay, this is how the y's are generated. Okay. So here the eta i's are IID according to a normal distribution of 0 mean and variance sigma squared. Okay, so the first question is whether so the least square solution, because I will write it many times, I will not put the LS, I will just call it W hat, but I'm always referring to the least square solution. Okay. Is W hat a biased estimator in this case? What does it mean biased? So you recall the bias variance trade-off. Biased means that in the best case, when we have access to infinitely many data, if there is a mismatch, there is still a difference between our estimator and the true one, okay, the true function. Here, the true function is linear like this. So essentially, we want to see that if our so is, I will write the question, is W star biased? Okay, so another way to recast the same question, okay, the bias would be 0 if the expectation, okay, with respect to the data of the estimator is equal to the true model. And the true model, in this case, the true function, okay, is this W true, okay. So I claim that if you write the bias from the definition in the bias variance, okay, you will see that this bias is 0 in this case if this is true, okay. This is a sub-exercise. Verify that this condition implies that the bias in the bias variance trade-off is equal to 0. Okay, so let's compute this expectation. And actually here, I will only compute an expectation with the noise. It will be sufficient. I could also take an expectation with respect to the data X, but this will not change anything. Okay, we will directly see that it's not biased anyway. Okay, so let's do that. I'm computing the expectation of what am I doing here? Yes, okay. So I'm computing the expectation of this estimator, whose definition is here. Okay, and now I can replace the y by its true form. Okay, it's generated like this. Sorry, X transpose, I miss here. X transpose Y, which is XW true, plus my noise. Okay. And this is the same as the expectation of X transpose X minus 1 X transpose X W true plus X transpose X minus 1 X transpose the noise. Okay. And I can, by linearity of the expectation, I can separate the expectation in two. Okay. And what do I obtain directly? Okay, this does not depend on the noise. So the expectation over the noise here acts only here. And because this noise has zero mean, this is zero. Okay. And this matrix is the identity. Okay. Because you see that I have X transpose X inverse times X transpose X. So what I just proved is that this is the same as W true. Okay, so in average over the noise, which means essentially the same as if I had access to infinitely many data points, which would allow me to average out the contribution of the noise. My estimator, okay, my parameters are the true ones. So there is no bias. Okay. And this was expected because we are in the realizable setting. Okay. Is that clear? So I will stop asking that question. Okay, I will sometime pause a bit for you to absorb. And, I give you the opportunity to ask a question, but if there is not, I will go on. It would be nice to have, you know, some basic interactions. I don't even see you.
In case we try to do the expectation on the X2.
Yes. Okay.
Yeah, I don't think the computation would be easier because I tried to solve the exercise from yesterday.
It's the same if I take the expectation with respect to X. You see that
yeah, because,
if you want, I can put an expectation over X everywhere here.
Yeah, but for the second term.
Yeah, but you will get here. What you get is you have an additional expectation over X here.
Yeah, but but it will go to zero.
But it will go to zero anyway.
Oh.
And you get an expectation over X here. So it's the same. This is why I said that you don't need to average. Okay. So very simple, but important to grasp. Let's do a slightly more technical question, which is a question I asked you to have a look some time ago. So we are still in the same setting, this realizable setting, okay, where the true model is linear and the noise is Gaussian additive. And what we want to compute is what I will call the in-sample risk, okay, which is closely connected to the expected training error. So when we say risk in statistics, what we always mean is the expectation with respect to the data, with respect to maybe all sources of randomness in the problem, but often we mean with respect to the realization of the data, the expectation of some error. Okay, so we define the training error, and the training error is a number that depends on the data. But if you think of the data as a random variable or a set of random variables, and you average this training error with respect to that, you get not anymore the training error, but the training risk. Okay, risk just means expectation of errors in statistics. Okay. So what I want to compute first is what I call the in-sample risk that I will denote R in, which is by definition 1 over n, where n again is the number of training points. And here I take the expectation with respect to the data, okay, of the train of an error, so a loss, a quadratic loss. And this will be, these are my predictions according to my model, okay. Minus the true labels, okay. So what is the difference with the training risk? Is that in the training risk, we would not here have just the true labels without noise, but we would have their noisy versions, okay. So it would be the wise train, and the wise train would be XW true plus the noise. So you see, there just would be the difference. The difference would be this noise. We will compute this training risk right after, but first we compute this simpler object where the noise is not present. This really measures the expected square deviation between your predictions according to this least square estimator and the true labels, okay, in the training set, okay. So it's 5:30, but let me take few more minutes because I was way too slow today, but I think it wasn't important for you to understand properly the Bayesian interpretation, which I think is really important. But I thought I would do it much faster. Okay, so again, here the expectation means with respect to the data, okay? So the pairs of inputs and outputs, the X and Y, okay? So let's compute this. So actually I will compute just the expectation. I will not carry this 1 over n everywhere, okay? So we want to compute this thing. So a norm 2, okay, a norm 2 for a vector is the same as the vector transpose itself, right? So I will directly write the vector transpose itself. And I will write WT for W true, okay, just to make things lighter. Now I will, okay, I will develop this square. What do I get? I get W transpose, X transpose, X W K minus 2 times W true X transpose X W hat plus W true transpose X transpose X W true. Okay, now I'm replacing my W hat by its solution, the solution of the least square. Okay, so let's see what it gives. I get, actually, I think I could have done much simpler, but here I will have many simplifications. Yeah, I think, okay, sorry. Let me do simplifications from the beginning. Here I will just make it more complicated than it should be. Let's see if I try in another way. I directly replace the W hat by its expression, okay? So it's the least square solution is X transpose, too many bugs, is So I have X and I have X transpose X minus 1, X transpose Y. Okay, yeah, this is the correct way. It will be much faster. Minus W true. Okay. And this is our W hat. Okay. And now I replace Y by the true model. So what is Y? We look at what is the model. It's XW true plus the noise. XW true plus the noise minus XW true. Okay. What do I get? Okay, let me expand a bit. Get X transpose X minus 1 X transpose X W true plus X transpose X minus 1 X transpose eta minus X W true. And this is 1, it's the identity. Okay, so this term is nothing else than XW true, which is also there with a minus sign. So these two terms, they simplify. Okay, so yeah, it was much faster. Let's see what we can do from here. We have to deal with that term now. Okay. Okay, so how do I do? What I will do is now to really expand the square. So this is the same as X transpose X minus 1 X transpose eta transpose. All that is a vector. I make it a row and I multiply by itself in the column form. Okay. And here I apply the rule for transposition. And what does it give? It gives eta transpose X, all this matrix transpose, but this matrix is symmetric, okay, because I take the inverse of a symmetric matrix, so it remains symmetric. So it does not change. And I have X transpose, and now I have all the other terms, X transpose X minus 1, X transpose eta. And now I see simplifications because this matrix, for example, simplifies with that one. Okay, it gives me the identity again. Okay, so all that is expectation of eta transpose X transpose X minus 1 X transpose eta. Okay, what is the next simplification I can do? So here is a trick that is extremely useful when you do linear algebra, when you manipulate matrices that you're probably not familiar with, but you should keep it in mind for the future. It's super useful. All that, okay, is just a number because, okay, I just did manipulations on this object from the beginning, which is a number. This is the norm 2. This is the norm of the norm square of a vector. So it's a number. Okay. So all that is a number. And indeed, we see a matrix applied to a vector. So it's a vector. So this is still a vector. This is a vector. So all that is a column vector. And here I have a row vector. So I have the inner product between two vectors, and this gives me a number. And when I have a number like this, I can just take the trace. Okay, so what is, do you know, is everyone familiar with what the trace is? So the trace of a matrix, let's say A, is by definition the sum of the diagonal elements, okay? And the number, all that belongs to R, is just a scalar, is a special case of a matrix, okay? It's a matrix with dimension 1 and 1, so it's just a number, okay? So I can put a trace here, okay? And this does not change this number, I'm just summing the unique diagonal element of this trivial matrix, so it's unchanged. But the trace has a very nice and powerful property, which is called cyclicity. Cyclicity, yeah, I think it's correct. So what is the cyclicity of the trace? Is that if you take the trace of a product of matrices, you can take this one and put it here before. So this is the trace of BA. Or if you have more, let's say trace of ABC, a product of three matrices, this is the same as trace of CAB. So you see, which is also the same as the trace of BCA. You can always take a matrix at the end and put it at the beginning, or vice versa. Take the first one and put it at the end. And this does not change the trace. Okay, you can prove it very simply by writing everything with components and using the definition of the trace. Okay, so and by the way, okay. So I have expectation of the trace of, I will leave some space, eta transpose X. And of course, here, A and B are not necessarily matrices of the same size. As long as the size match in a way that you can put B in front of A, that this is well defined, it's okay. So for example, here we are manipulating inside this trace things that are matrices like the X's and vectors, which is this eta. Okay, but you will see the manipulation that I will do. It's allowed because the dimensions match. So what I will do is that I will take the last one, which is this vector, and put it there. Okay. And I get, and this trace, as you see, is a linear operation. Okay. So trace trace of A plus B is the trace of A plus trace of B. Okay. And the expectation is also a linear operation. Okay. The expectation of A plus B is the expectation of A plus the expectation of B. And when you have two linear operations, you can exchange their order. You can do one and the other. You can do first operation first and second, or vice versa. You can change the order. Okay. So all that is the same as the trace of the expectation of eta transpose X, X transpose X minus 1, X transpose. Okay. And this expectation is acting on the noise and on the X independently, because the noise is of course independent of the X. Okay. And actually, here, let me even take, let's say that the X's are fixed, just to simplify the idea. We can just average over the noise. It's fine. We will obtain what we want. Okay. Like before, it does not change anything. So this expectation only acts on this matrix here. This is a matrix of rank 1. Okay. This is a row vector times a column. So this forms a matrix of rank 1. Okay. And what is the expectation of this matrix? Concretely, what is this matrix?
Sigma squared.
If I write it, yes. So let's, I think you got the answer, and I will write it explicitly. I will write this matrix element wise. What is this matrix? So this is the expectation of the matrix whose element ij, whose entry ij is eta I, eta j. Okay. And what is the expectation of this thing? It is 0 if I is different than j, because two realizations of the noise are independent. Okay, by assumption here, the noise are independent and with 0 mean. So if I take the expectation of eta I times eta j, this is the same as the expectation of eta I times the expectation of eta j, and both have expectation of 0. So when I is different than j, I get 0. Instead, if I have I equal j, this is the expectation of eta I to the square. And because these random variables have 0 mean, this is the same as the variance. This is just sigma squared. So all this matrix is the identity, okay, of size p times p, okay, because eta is of size n, times sigma squared, okay? And therefore, all that gives me the trace. I can put the sigma square outside, the trace of x transpose x minus 1 x transpose. I use again the cyclicity of the trace to put, for example, that one here. And it gives me sigma square trace of x transpose x minus 1 x transpose x. And this is what? This is again the identity of size n times n, and the trace of the identity. I'm summing all the diagonal elements of the identity of size p, of size n. Sorry,
The other identity.
One second. These things are of size. Yes, n. I'm not doing any mistake. I'm doing a mistake. I was expecting a p somewhere.
But the identity n by p.
Yeah, but I'm missing a p here. 1 second. No, but okay, here it's n times n. Not an identity is always a square matrix. 1 second. How do I get the p at the end? I did a mistake. No, sorry. This is
P by p.
This is a p by p. I'm sorry. This matrix is the identity of size p by p. Okay, the matrix X is of size n times p. So X transpose X is of size p by p. Okay, and so this is sigma squared. So the trace of the identity of size p is just p. Okay, so what we obtained, that R in, now I need to divide by n. Okay, recall the definition of R in, there was a 1 over n in front here. Okay, while what we computed is just the expectation. What we obtain is sigma squared p over n train. Okay. I was going to say very simple. That's not true. If you've never seen this kind of computation, it's not simple. You have to absorb it and to try again by yourself. But once you know this trick of introducing the trace and using the cyclicity of the trace and the linearity of the expectation and of the trace, then you're done. Okay. At the end, it's not so complicated. And here you have to compute this expectation and realize that by independence of the noise, it's related to the identity. Okay.
Can I ask something?
Yes.
Because you said that the expectation of eta transpose is this ID n by n times sigma squared.
Yeah, but it should be a p by p.
Because
No, it's correct. It's correct.
yeah,
It is
when you
this matrix is n by p. So this matrix has to be n by n. Otherwise, there would be a mismatch in dimensions, right?
yes, but when you get you are supposed to get the trace of the whole, right?
Yes.
There should not there is no n.
No, because here, once you have that this expectation is the identity, okay, this identity is just multiplying this matrix X, and so it's unchanged.
Okay.
It's absorbed in the X if you want. It's just
Okay.
okay.
Okay. I thought that you will still get the trace of this whole.
No. The trace is the trace of the
Okay.
whole product.
Yes.
And this whole product leads to a trace of the identity of size p by p. Okay.
Okay.
So now if we define really the training risk, and I will not redo all the computation, but it's exactly the same, which now really is the expectation of the xw least square minus the y's. Okay. What is the y? Again, you replace the y by xw true plus noise. Okay. You see that we already computed a big chunk of it. This is the same as the expectation of xw minus xw true squared plus norm of the noise squared plus 2 times trace of xw at minus xw true transpose the noise. Okay, we already computed this part. This is it. Okay. This part is very simple. The norm of the noise is just the number of points times sigma squared. And now we just have to compute this by the very same manipulations as I did before. It's exactly the same computation, and I advise you to do it. And at the end, ... what you obtain is the formula that I gave you at some point, is the sigma squared 1 minus p over n train. So please fill in this ... just to compute this term, to check you understood how we did for this first term. It's exactly the same way, and you will obtain this term here. By exactly the same way, I mean that you only need to introduce the trace, use the cyclicity, and realize that when you have an expectation of eta transpose, it's linked to an identity. Okay? So try to get that. And again, by the same computations, you can get exactly in the same way. There is no difference than the expectation, so the prediction risk, so the expectation of your estimate on the new fresh samples in the test data, okay, is sigma squared 1 plus p over number of test points. Okay, here there is an assumption is that the test data is made of the same inputs as in the training data, but the only difference are the outputs y tilde, which are just, the only difference is that the noise are new realizations of the Gaussian noise, but the inputs are shared between the train and test set. So this is not very realistic, but this is how you can get this thing, this formula that we analyzed. And you remember, by comparing this training risk and this test risk or prediction risk, we understood that we have no overfitting when n, okay, and in this case n test is equal to n train because the x is shared in both cases, so we just write n in both cases. When n is much bigger than p, we have many more data than the number of features. These two errors, they converge to the same number, which is sigma squared, which is the irreducible error. Okay, so there is no overfitting. Okay, if instead p over n is rather large, you have a big difference between the training risk and the prediction risk, and you are in a regime where you have strong overfitting. Okay, you remember these discussions we have. So please try to understand these computations we did today. These are probably the most technical computations we'll do in this course, but I think it's important that you know how to manipulate some linear algebra like this, and also it makes you understand what is going on. Sorry for the delay, but I really had to finish that today, and I'm done. So if there is any question, let me just mention that tomorrow we'll start directly by discussing the notebook 4. So I invite you to understand. It's not tomorrow, sorry, it's Friday. Friday we'll start by discussing the notebook 4, which is again linear regression, but on a very nice application, which is how to learn the Ising model from configurations from the Ising model and from energies. So the inputs are random configurations of the spins, and the labels, if you want, are energy levels. Okay. And from this data, we want to learn the Hamiltonian of the Ising model. So it's a very beautiful application, I think. It's very nice, and so it would be a shame not to try by yourself a bit before. And then we will study logistic regression. So how to not anymore regression with linear models like this, but another type of regression, which is actually used for classification. This will be a classification problem using a different type of models and costs, and I will also discuss gradient descent. So logistic regression and gradient descent will be done together, but before that we do this this notebook on the Ising model. Okay. All right. So if there is no question, is there any?
No question.
Okay, thanks. All right, so again, for those who want to come by my office, do not hesitate, okay? I'm there every day. All right, I think now the videos are on the YouTube channel, huh? So I asked the staff to put them so you can check the previous videos if you want.
Yes, thank you. They're online.
Okay, great. So see you everyone, see you on Friday. Enjoy your week. Ciao.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye.